Right, welcome to lesson 4 of the UCal4 training class. This one is on qualitative data analytics. This is a very fascinating, very interesting part of chemometrics and part of UCal software. It is pretty new to Unity Scientific. We've got a couple of customers that are using this right now. I have worked on this with multiple other customers in the past. There are some really interesting applications here, and I think with the focus on food safety and the food security and protection that a lot of producers are focusing on right now, that this is a very useful part of our software. And one of the really nice things is that you can set up your SpectraStar to do quantitative models and then have a qualitative model just on top so that it does some sort of a pass-fail or something based on other criteria. So with that, we will jump into qualitative data analysis. All right, lesson 4. So a lot of the investigations, a lot of the evaluations that we're going to be doing when we're talking about qualitative analysis are going to be based on similarity measurements. So we're trying to figure out, are these two samples similar, or is this sample similar to a group of samples that I've seen before? If the spectra are similar, we're going to assume that these samples are similar. So this goes back to how we ended our last lesson when we were talking in quantitative data analytics. I also feel I call this a spectra first perspective. And our approach to dealing with a lot of this modeling, quantitative and qualitative, and our population structuring and our outlier determination is based on investigating the spectra first. Because we're trusting that where the spectral variability leads, our sample variability will follow. And we're going to be doing that also in qualitative analysis. There are two different ways in general, two different scales, ways that we can evaluate similarity. One is a distance measurement, and the other one is a correlation type measurement. So with a distance measurement, a perfect match is a distance of 0. So my unknown sample has a distance of 0 from a previous population. It's very, very alike. For a correlation measurement, we are looking at how similar we are, but we are using a relationship between our sample and those, with a value of 1 indicating a perfect correlation or very high correlation. So these are just two different scales, two different ways of describing similarity between samples. So as an example, correlation has a perfect match of 1. And again, distance measurement, a perfect match is approaching 0. And these are two different formulas for calculating these. I will not describe these. We can also describe distance, the second one, in terms of an arc cosine. And this is based on a mathematical formula called cosine similarity, and it's one of the algorithms that we use when we are doing qualitative analysis. So we find similarity in all sorts of different places in UCal4 and in our calibration development. We can use it in our quantitative models. We use it for our outlier indicators. We talked about that last lesson. Global distance, nearest neighbor distance. We will use it in population structuring. This will be an exercise in the middle of our course, in the middle of our exercises. We will be using this similarity to determine unique samples, in other words, ones that are not similar, but we will also use it for finding new non-similar samples. So we will be able to determine and be able to manage our calibration expansions very efficiently based on similarity measurements. We're also going to use it in qualitative models. And this is sometimes called good product, bad product, good samples or bad samples. So we will use these types of measurements in multiple areas. So qualitative models usually rely on a set of samples that we deem good or of a proper behavior. So the training set must contain a representation of the entire variability that we describe as good. So this should not be just a single sample or 2 or 3 samples. We want a group of samples that will encompass the variability that we deem good or appropriate, that we want those samples that express this variability to be termed and to be classified as good. How we classify that, we will determine which scale we're going to use or which metric type, either a distance or correlation. And depending on that, whichever metric we use, we will also want to send a limit or a threshold for where good would be set. In the background, all of these measurements are actually numeric measurements. We're measuring a degree of similarity, and then we are determining a pass or fail. So different types of qualitative analysis. One of the most common is, does this sample belong to class A or B? This could be used as a product determination to determine what type of a grain it is, some other different classification. We can also determine, does this sample belong to a particular defined classification or not? So this is, am I good? Or am I, for some reason, not good? Do I not belong? Finally, we can look at which of many classifications or which of many groups does this sample belong the best? Which group am I most similar to? For all of these, we want to figure out how likely is this assessment correct? So, and again, I just said that all of these evaluations are numeric based. So we will do this based on threshold limits. A couple of the nice things about qualitative analysis. Number one, you do not need lab values. When we were talking about quantitative analysis in our last lesson, I was discussing reference value budgets. And I think that that's a very typical scenario. I remember when I was making calibrations, I would go in and I would say that for this year, I have a budget of 120 reference analyses. How can I spend that budget the most wisely? Well, if we've got knowledge about our samples, if we've got knowledge that says that these samples are good for whatever reason, they produced a good product. If we know that these samples are good, we can start our qualitative analysis project and calibration without any reference values at all. We just need to be able to assign either a class membership, product A, B, or C, or we need to be able to assign good versus bad. Another useful thing is we can use conformity analysis or good product, bad product to look for contaminated samples or adulterated samples. This has a lot of food safety implications. If we know what the contaminant is likely to be, we can restrict the wavelength range of our qualitative investigation. A classic example here was melamine in milk powder. In the early 2000s, I believe, or around early 2000s, there were a number of different scandals around where melamine was being used to spike milk powders. And melamine conveys nitrogen into milk powders. It raises the nitrogen level, and for various protein assays, which are just measuring nitrogen, it can fool those assays into reporting an elevated level of protein. The melamine, unfortunately, created a poisonous situation, and especially for pets and for people. Well, melamine has a very specific peak in the near-infrared spectra. And once it was determined that these adulterations were melamine, it was very easy to set up a qualitative model restricted to that wavelength range where that peak was, and you could very reliably pick out melamine-spiked milk powders based on a quick qualitative model. So that was a case where if you're looking for a specific contamination, you can really zero in your qualitative evaluation. Another nice thing is that this gives a pass-fail reading. You can set up UScan to use a qualitative model, do a pass-fail, and right away your operator knows, yes, this sample passed, or no, it failed, and some further investigation is needed. And lastly, it relies on the idea that good samples have good spectra. So the spectra first approach that we are talking about throughout this course. One of the measurements we want to make is a discrimination. Does this sample belong to class A or class B? This is one of the easier ones to do. It can be done with a quantitative method. We're going to do this in one of the exercises, and we will use this to determine between hard and soft flour. One thing to note, and this is typical of all of our qualitative analyses, but we do need samples of both product A and product B, and we need to know the distinction, be very sure about our classification. So basically what this evaluation does is it looks at your unknown samples once you've created this model, and it determines the similarity to product A and the similarity to product B. And you are determining which one it is more similar to. Another common assay or common investigation that we do in qualitative analysis is conformity. And I've seen this done in several different ways. I think this is extremely powerful. If anybody is interested in setting up a conformity test, I would love to work with them on this. I find these very interesting. But basically what we're saying is, does the sample belong to this defined classification or not? I sometimes think of this as a good product, bad product. If your unknown sample falls within the specifications, within the limits of this test, we deem it good. If it falls outside, we don't know why. All we know is that for some reason, this sample does not match and does not conform to what we have deemed a good product. So it does get a little bit more complicated because determining that limit can be a little bit difficult. So our unknown samples can either be evaluated and the results can be predicted either in the form of a probability or a standardized value. So this goes back to our distance versus our correlation that we were talking about earlier. If we are using the probability type of result, 1.0 is perfect. Okay, this is similar to a correlation of 1. If we are using a standardized value, 0 is perfect, and there's no limit. So the further that we're getting away from 0, the more dissimilar we are, and the less our sample is conforming to the good product. So if we are using a standardized value, we need to set a limit from 0 that describes our boundary between a good and a bad product, or a pass and a fail. So during prediction, we compare this to the average spectra and the the evaluation that we've set up in the training set, and then we do this similarity or conformity measurement. Okay. One of the ways that I saw that this was being used in the past was for bakery mixes. In a bakery mix, there was not a lot of value to trying to predict individual quantitative constituents. So there was no moisture measurement, there was no ash or protein measurement that was useful or needed for bakery mixes. But one of the things they wanted to know was, did my bakery mix in powder form look like it was supposed to? Did it have all of the right ingredients so that I can be reasonably sure that when I run through my entire production and I make my rolls at the end of this, that they are going to be a high quality product. So basically what this customer was doing is they were analyzing a number of samples from good mixes, from good batches. They were describing this population as a pass. And if there was ever a case where a batch was made that was missing an ingredient or two, it would fall outside of that conformity and it would be flagged as a fail. Further investigation needed. And the payback for this sample was, for every batch that they caught before they went through the entire production run, it saved them hours and hours and huge dollars running through the entire production, only to have, pounds and pounds of rolls that did not meet their final spec. So it was learning and predicting production failures before they spent all the time and effort and resources into it. That's a very good example of where a conformity product can really help you. Another one is product selection. To which of many classifications does this sample belong? The way that we do this right now in UScan is to have multiple conformity models, and we're looking for the one that is closest, that passes the most. For this one, you need to describe each product group explicitly beforehand. You need to know that I'm looking at 4 different products, A, B, C, and D, and you need examples of each of them. There are other ways to do this, from an automated perspective. I am also interested in any customers out there or any applications doing product selection. This is something we're looking into in our product development. There are a lot of different options when you get into product selection. So if there's anybody out there that's interested in doing product selection, I would also ask them to contact me. We'd love to hear their ideas and work with them as we're integrating this into our software, our routine analysis software. So for all of these different models, one of the things we want to know is, how accurate is this evaluation? How likely are our classification assignments going to be correct? If we are doing good product, bad product, how often are we catching bad products, for example? Being correct is nice, but there are other issues that creep in. And one of the things that we find, especially since, remember, this is all numerical based in the background, is that there is room for error and there are some gray areas in here. When you are setting up a qualitative system, one of the things you need to think about is, what are the costs of a false positive or a false negative? So if you are getting an improper classification, what are the consequences of erring in one direction or erring in the other direction? This is a consideration that you might want to take into account when you are setting your limits. So validation sets are especially important for qualitative models. You really want to make sure that you've got independent validations for your qualitative models. Finally, these models can be used for screening. I described the bakery mix example before when it was coming to conformity. As soon as they had a fail, the first thing they did was go in and investigate and take a second look at the bakery mix. So understanding that these classifications are based on limits, these limits are in gray areas. How you react to a fail is very important. But at a minimum, one of the things it can do is put that hand up and say, hey, we've got a potential issue with this sample. We need to investigate this further. So talking about limits and how accurate these can be. If we are looking at standardized units, we've got 0 being a definite pass. You won't find those in routine analysis. You will always be away from 0. With very large numbers, 100 or more, even 20 or more is a definite fail. But in between that, how do you set your limits? Based on the training set, this is how your standardized units will go. That distance of 1, this is, our distribution is 67% frequency, 2 is 97, 3 is 99% frequency away. So this is a way of setting the thresholds. And one of the nice things about standardized units is, to me, this is a scale that is understandable. It's also generally numbers that are very easy to interpret. We can also look at our results and we can report them out in probability units, where 1 is a definite pass. Again, you're not going to get a 1 value, but you might get numbers that are pretty close to that. On the other extreme, a 0 is absolutely no probability, no correlation. So that's a definite fail. But where does your threshold fit? For a number of different analyses that I've looked at, the threshold is fairly high and it's fairly narrow. And you're going to be working with a number of significant digits to be able to set your threshold accurately. So it might be 0.995, it might be 0.978. This starts getting into a scale for me that is less obvious, less intuitive to work with. But there might be some cases where probability is the way to go, or your processes, your procedures, your SOP, your operators just understand a probability unit better than a standardized unit. For this reason, we offer both, and we offer the evaluations and the reporting of our qualitative models on either a standardized unit or a probability unit basis. These two methods are related to each other, and these formulas below relate how you can go from one to the other one. Once you've decided what metric you're going to use, what your thresholds are, one of the things you really want to do is to go in and validate your model. So how do you evaluate your qualitative model accuracy? To do this, what you need to do is you need to compare your accuracy and looking at your true results and comparing them to your false results. And this is done typically and classically by the use of a confusion matrix. And you've seen where in these lectures, we like to use Wikipedia. You can go in and look at confusion matrix in Wikipedia, and it describes this is a system of 4 possible outcomes: a true positive, true negative, false positive, and a false negative. And what you are looking for is comparing your true results to your false results. Accuracy is your true results over the total. To repeat, the accuracy fraction is the trues over the total number of samples. The classification error fraction is 1 minus this number, so it's just the opposite. One of the major concerns and one of the major difficulties in qualitative analysis are these marginal samples, the ones that are in the gray area. And your test set is really going to help you set your limits to make sure that these gray area, these middle samples are dealt with positively. And also, as I mentioned a couple of slides ago, based on your situation, you might have a vulnerability, a cost, a liability of being a false positive or a false negative that influences where you want to set that limit. So in your situation, you might want to err on the side of caution and set your limits so that you have more false negatives to make sure that you catch a certain condition, for example. No matter what, in virtually all cases, you will have these on the border samples. So again, setting these limits will reflect the requirements of your particular analytical situation. The confusion matrix looks like this. So we've got a predicted condition and our true condition. So this is the actual condition. So if the condition is positive and we predicted it positive, we've got a true positive. Those are great. The condition is negative, we predicted it negative, we've got our true negative. Those are the results we want. The errors that we want to look for are false positives. So we predicted it positive, but it was in fact negative, or false negative, where we predicted it negative, it was in fact positive. These are type 1 and type 2 errors. I think this is also a typical example. I've seen this from multiple different areas, but sometimes people talk about a guard dog as being an alarm. So in this case, we've got a situation where we have a guest or we do not have a guest, and the dog barking is our indicator. So a true positive would be a dog barks and there is an unwelcome guest that's out there. A true negative is that the dog does not bark for a welcome guest. So the welcome guest is there, but the dog does not bark. A false positive is the dog does bark for a welcome guest. So this is a type 1 error. And a false negative is the dog does not bark for an unwelcome guest. Okay, so the dog is the discriminator as to whether or not the guest is welcome or not. And if the dog is correctly picking up as to whether or not the guest was welcome or unwelcome, we get a true result. If the dog is wrong, we get a negative result. And the accuracy can be calculated here. So for qualitative evaluations and determining the accuracy and the limit, a couple of cautions. The accuracy computation normally comes only from a validation set. I would not do this based on your training set at all. You really want to have a completely independent validation set to make sure that your limits are set up properly. The degree of accuracy is going to be based on your marginal samples, or the ones that are in these gray areas. And some of the times these gray areas have a lot of samples in there. And again, you need to understand what are the costs of being wrong in one way or another and set your appropriate limits. And this is your false positive or false negative penalty ratio. So if you have too many false negatives, so they're samples that are in fact positive, but they've been labeled negative. What you want to do here is to raise your action limit. There is also a mode in our software that you can set this based on a ratio. It's auto mode. So in this case, you would use a lower ratio and move your limit down, or move your limit up, but use a lower ratio. Conversely, if you're getting too many false positives, So these are situations that were in fact negative, but they've been labeled positive. So false positives. In this case, you want to lower your action limit. Or in auto mode, you're going to use a higher ratio. So in this way, you can determine your threshold, determine your limits, and make sure that your analytical situation and your qualitative analyses are pulling out and identifying your fail and pass samples correctly according to your analytical needs. Okay, and that's the end of the qualitative data analytics lesson. We will now be working on moving on to the exercises. Just a quick note about qualitative data analytics. I think this is a very exciting part of near-infrared evaluations. There are a lot more variables in this. It's not as straightforward as doing a simple quantitative evaluation and a quantitative prediction of a constituent. There are more questions, but there are also more possibilities. And I think in today's environment of food safety, there are a lot of great applications out there. And I would just like to remind everybody that you can add a qualitative model on top of your existing quantitative setup. So this can just be an additional parameter for your operators. All right, that's the end of qualitative data analytics. We're going to move on to our exercises now. Thank you, everyone.